Hello everyone, welcome back. This is a follow-up video to what I have already discussed in drift velocity video. I had made two claims there that we can prove, and this is a follow-up video where I am going to prove those two things. The claim that I had made was average time since last collision is not same, but it is equal to relaxation time. Relaxation time is the average time between two successive collisions, and the average time since last collision is slightly different. There is a slight variation to it. Most of the standard books, they do not give a satisfying explanation as to why they are equal. Suddenly they transition into relaxation time, and that is something that I have observed. So I am going to prove that mathematically, and also other claim that RMS value of time since last collision is going to be root 2 times mean time. That is also something that I have to prove. So this is going to be mathematically a bit rigorous. Please bear with me. I am sure you will definitely appreciate it. So before going for the derivation, the standard assumptions that we made in this Drude's model, for me the source is Feynman lectures, and this Drude's model has been explained pretty well. And the assumptions are this: free electron gas, number one. You see, free electrons are very large number in conductors, 10 power 28 per meter cube. So if you want to understand the number, just understand the number of people in the world. World population is probably 8 billion. You take 10 billion also, that is basically 10 power 10. Compare 10 power 10 with 10 power 28 per meter cube. That's humongous number, huge number of electrons. It's like you have cloud of particles which are moving in all directions randomly inside the lattice. That's why we call it as electron cloud. And electron cloud is taken to be classical gas, like you have kinetic theory of gases, ideal gas. So there actually there won't be any interaction between the molecules. Here you have electron charges there, but we neglect that. That is assumption which H. was pointing out. It is gross approximation. Yes, that is assumption we have taken. And the next one is the ions movement. They oscillate, yes, but the oscillations of the movement is negligible compared to the motion of the electrons. That is the second assumption we take. And the electron-electron interaction, electron-ion interaction is not considered except during collision. Electron-electron interaction anyway we do not consider even during collision. We neglect the collision between electrons because their velocity collision, they just exchange their velocities. There won't be any effect there because of it. Next one is randomizing collisions. Whatever is the ordered velocity because of external electric field you have, once the collision happens, it gets dissipated into random velocity. There won't be any memory of ordered velocity memory. So you will have to start again all over fresh after the collision. So that is the assumption we have taken. That's okay. Mean free time, in the sense average time between two successive collisions, is assumed to be constant because we assume the lattice structure to be uniform, temperature to be uniform. Under that assumption, tau would remain the same. And then classical mechanics, we assume that Newton's law is valid, probability ideas are valid, kinematic equations are valid. So these are the assumptions we have taken here, and with that assumptions we are going on ahead. So the next one is, there is the one relation which I have to prove. If I know this formula, then proving whatever my claims, right, would be just mathematical. But this we need to prove. And here first of all, n equal to n naught into e power minus t by tau. You know tau meaning relaxation time or mean free time. Small t is the time since last collision, and n naught. N naught is the number of free electrons which had experienced a collision at t equal to 0. There are so many electrons, 10 power 28 odd, something like that. Out of that, n naught electrons experience collision at t equal to 0. Now out of that n naught electrons which experience collision at t equal to 0, how many electrons would survive without further collisions up to t time? That is n here. N and n naught relation we have, this is exponential decay we have it. We have to prove that first. This proof will go in 2 steps, in fact 3 steps. So first 2 steps will actually create the premise, and third step would be mathematical. First, step 1 about this relaxation time. You consider one electron for a long duration, and in that very large number of collisions would happen, some let us say eta naught. Total time is t naught, t naught by eta naught is the relaxation time. So that means let us say relaxation time is 1 nanosecond, for example. That means after every 1 nanosecond, on an average, an electron will experience one collision. That doesn't mean that strictly every nanosecond it is going to experience one collision. In 1 nanosecond it may not have any collision. In other nanosecond it might have 2 or 3 more collisions there. So, but on an average, if you take the overall about 1 hour, if I take, in that 1 nanosecond is nothing. In that, on an average, 1 collision per nanosecond, you can see that. That's a assumption we are taking here. Now, let's say N naught, capital N naught electrons are present there in the entire lattice there. And if I consider delta t, one time interval of tau nanosecond, in that 1 nanosecond, does it mean that every electron will experience one collision? No, not necessary, because it's all random. But if I take all N naught electrons, which is 10 power 28 per meter cube, whatever it is, definitely I can say that one will have no collisions, one will have maybe 4 or 5 collisions. So on an average, each electron would have experienced one collision in that time interval tau. So the average collisions per electron during the tau time will be equal to 1. That is the assumption there. I hope you understood that assumption. It's a very simple logical. So that is the first step we need to understand. On an average, in a time interval of tau, one collision will happen per one electron. One electron may have more collision, other electron may have less number of collision, but on average this many collisions per tau we have it. So that is first step. Then we will go for step 2. Step 2 would be about probability of survival. Survival meaning with avoiding collisions. Probability of surviving of that ordered motion we are talking about. So here we have two hypotheses. We say that, let us say collision happened now, next it is travelling for delta t. More the time it travels, more is the likeliness that it will undergo one more collision. Assuming the lattice structure is uniform and the temperature is uniform, more the time it travels, more is the likeliness that it will undergo collision. So that is one first hypothesis. The probability of a collision happening, it depends on how much time it travels. So that is first assumption we have it. Second hypothesis is that if I take tau time, delta t equal to tau time, the number of collisions would be 1. That means the probability that one collision happens is 1. Probability is 1. Definitely, certainty, with certainty we can say that on an average, one electron will undergo one collision. On an average we are talking about. Probability is always on an average for a large number of trials there. So that is what we have. So probability for delta t of collision is 1 collision, and probability is proportional time interval. Now combining 1 and 2, if I consider dt time, and you have N naught electrons, so many electrons are present there. In this dt time, what is the probability that an electron will undergo one collision? So tau time corresponds to one collision, then dt time corresponds to how many collisions? So it is going to be proportionality there, time ratio dt by tau. That is the probability that an electron undergoes one collision in the dt time is what I have. Now probability of survival. So if one collision happens in this interval, then what is the probability that no collisions happen between that? Is the total probability 1 minus the probability of collision dt by tau. That is what you have, probability of survival. So that is step 2. Once we understand the probability, then it is step 3 is going to be mathematical. Let us say you have N naught electrons which experience collision at t equal to 0, and they were surviving, some of them survived and some of them are continuing to have more collisions. At t time, let us say n of t you have, which did not have any more collisions after t equal to 0. Now if I go for t to t plus dt, that is some small time interval, how many more collisions will happen, and after that how many will survive? That is n of t plus dt. How many will survive after t plus dt? So that is what you have, n of t before the event happened into the probability of survival. I take from equation of 1, you get that relation. So after that you have to simplify it. N of t plus d minus n of t is nothing but dn. So you take dn by n and integrate it, you will get n equal to n naught into e power minus t by tau. Simple integration, logarithmic function, you have it. So with that, this formula has been derived, where n is the number of collisions, number of electrons which did not have any more collision after t equal to 0. They experienced collision at t equal to 0, but up to t they did not have any more collisions. N naught is the total number of electrons which experience collision at t equal to 0. So that is the derivation we have here. Now we go for the whatever claims that I had to prove that. Now we are ready to prove the two claims. Number 1, to prove that average time since last collision equal to relaxation time. First I have to take a definition, statistical calculus definition. average of y over x is nothing but integral y dx by integral dx. This is weighted average. We in 10th class, up to 10th class, we talk about simple average. Here we give weightage here. For example, center of mass is weighted average with respect to mass there. So weighted average is what we take here. Then by simply substituting y as t and x as n over the number we are dealing, integrating it, averaging it, you see that integral t dn by integral dn is what you have, and simple integration you will get e power x into e power x dx integration. You will do integration by parts. So uv dv minus uv minus u dv, right, integration you will have it. So that if you simplify it, you will be able to do it very easily. You can just take a screenshot if you require. Simple mathematics, simple calculus part, you have it. The next one is the important one, T RMS equal to root 2 tau. If you get that only, we will get whatever E tau by m, even with H over mass derivation there. So definition is what? RMS value meaning first you take the average of the squares of the time and then take a root. So average of the squares of the time is a simple, again same definition, integral t square dn by integral dn, and then simple manipulation there, alright. You see that it will come out to be integral x square e power minus x dx form there. It is a standard formula in definite integration. It will come out to be 2 factorial into x power 3 you will get. So you can just substitute there and you will get that RMS value of t is nothing but root 2 times of tau there. So with that I have completed the proof. So if you have any claims, doubts in it, you can definitely post message on that. So I will conclude here. Thank you very much for your time. Until next time, goodbye.